Good morning, students. So myself Akshay Mahendrakar, and we were in discussion with fluid mechanics. Correct? No, that is nothing but fluid dynamics. When the fluid is at rest, so what is streamline flow? Correct? Na? What is steady flow? What do we mean by streamline? And what is turbulent flow? Okay. And again, what we had discussed, what is critical velocity? Okay. And moreover that, again, one more thing what we had discussed, that is nothing but what? Equation of continuity. Okay. So in today's class we are going to discuss about one of the most important concepts in fluid mechanics, that is nothing but Bernoullis Principle. Okay, Bernoullis Principle or Bernoullis Theorem. Clear? So, according to Bernoullis Principle, that statement first I will tell you, then we are going to derive that complete derivation. So, the statement of this Bernoullis Principle or Bernoullis Theorem will go in such a way that in a steady flow, okay, in a steady flow means, what is the meaning of steady flow? At a given point, velocity of all the particles of the fluid which is passing through that particular point will be having same magnitude and direction. Correct? No? For all particles at a given point, magnitude will be same as well as direction will be same. So along a streamline, sum of pressure, okay, sum of pressure and kinetic energy per unit volume and potential energy, that is nothing but gravitational potential energy, will remain constant. Okay, that complete sum will remain as a constant one. So again we are taking a very cross-sectional pipe like this. Clear? It is having different cross-section. Where we had used like this derivation, we had used it in equation of continuity. Correct? No? So Bernoullis principle, it tells us P plus half rho v square plus rho g, which is equal to constant. Clear? Sum of pressure, okay, then kinetic energy per unit volume, next gravitational potential energy will result as a constant value. So what they will tell means, first of all, it is a very cross-sectional pipe, okay, of having cross-sectional area A1 at the end A, and at the end B we have one more different cross-sectional area, that is nothing but what? A2. Clear? So this is nothing but what? A2. Then here we have velocity of the particle at this point, it is nothing but V1, and again at this point it will be V2. Correct? Next thing what we are going to discuss here means, from the ground level, okay, from the ground horizontal level, this cross-sectional area is at height h1 and it will be at height h2. Okay. So how we are going to derive this? Clear? First of all, work done by the fluid particle at this point. Okay, basically work is nothing but what? Work is nothing but force into displacement. Correct? No? Force into displacement. So force and displacement, we are going to change these. That means in the other format we are going to write. So basically we know that pressure is nothing but force applied per unit area. Okay? Pressure is nothing but F by A. From P is equal to F by A, if I separate F means what I will get over there? F is equal to P into A. Correct, no? So therefore, I will write here F is nothing but P into A. Next, this is nothing but what? Displacement. Force into displacement will give us what? Actually work done. So work done by the fluid particle at this point, it is nothing but F into S. Okay? F is nothing but PA. How? Because pressure is nothing but what? Force divided by area. Pressure is nothing but what? Force divided by area. So it implies force is equal to pressure into area. Okay? Force is equal to pressure into area. Okay? Next, about displacement. Listen. We know that velocity is equal to displacement by time. Correct, no? V is equal to displacement by time. So we want displacement. How I can write? Velocity into time. Correct, no? So V into, for time I will be mentioning delta t. Okay? And this we are considering this as one phase, this as one more phase. That's why for these phase I will mention P1, A1, V1 into delta t. Clear? This is nothing but our W1. Clear? W1 is nothing but what? P1, A1, V1 into delta t. So now concentrate on this part, A1, V1, delta t. A fluid which is entering in a cross-sectional area A1 with velocity V1 in time interval delta t. Okay? So a velocity with a fluid particle with velocity V1 moving in a cross-sectional area A1 in a time interval delta t. Okay? Okay? Now carefully observe this A1, V1, delta t. So this V stands for velocity. Okay? I will be mentioning with small v like this. So a fluid particle with velocity V1, okay, moving in a cross-sectional area A1 in time interval delta t. This is nothing but what? It is nothing but volume. Clear? So W1 is equal to P1 into delta V. Okay? Similarly, W2 is equal to P2 into delta. So net work done is nothing but W is equal to W1 minus W2. W1 value what we are having? P1 delta V. W2 value we are having? P2 into delta V. So delta V if we take common means what I can write? P1 minus P2. P1 minus P2 into delta V. This is nothing but what? Net work done. Work done is equal to P1 minus P2 into delta V. Clear? Next, the gravitational potential energy, okay, it is given by delta U is equal to rho G H2 minus H1 into delta V. You have to remember this. Clear? Delta U, change in gravitational potential energy. This is actually change in gravitational potential energy. Change in gravitational potential energy is equal to delta U is equal to half G. Delta U is equal to rho G H2 minus H1 into delta V. Clear? So next, change in kinetic energy. Change in kinetic energy. This is nothing but what? Delta K is equal to, so we have half, okay, m v2 square minus v1 square into Okay, complete. Half m v2 square minus v1 square. Now from density relation we are changing this mass. So we know that density is equal to mass by volume. Mass is equal to density into volume. So delta K is equal to half. Okay, in the place of m what I can write, rho is equal to m by v or m is equal to rho into. So rho into, for v we are considering a small volume element. That means initially when this work can happen, this fluid will travel up to some point. Okay, here one more circle, if cross section if we will take means this complete fluid will come up to it. And here also, first we will consider over here, then we are going to taking it back, is coming here. So half rho into delta v into v2 square minus v1 square. Yeah. So by applying work energy theorem. Okay. Work energy theorem is nothing but net work done should be equal to sum of kinetic energy, change in kinetic energy and change in potential energy. Yeah? So by applying work energy theorem, what we can write means, first of all, our net work done. Net work done value is nothing but what? First I will write it with W is equal to delta U plus delta T. Yeah? So W value now substitute P1 minus P2 into delta V. P1 minus P2 into delta V is equal to delta U value what we are having? Rho G H2 minus H1 into delta V. Rho G H2 minus H1 into delta V. Delta V. Clear? Next, plus change in kinetic energy. Okay, plus half rho delta V, half rho delta V into bracket v2 square minus v1 square. Okay? So first of all, what all the things will cancel? Delta V will get cancelled. Here delta V. Now, shall I erase the board, this part? Okay? What is remaining? P1 minus P2 is equal to rho G H2 minus H1, correct now? Rho G, otherwise you can multiply rho G inside. Rho G H2 minus rho G H1. Okay, rho G H2 minus rho G H1 plus half rho V2 square. Half rho V2 square minus half rho V1 square. Okay. Now take all this 1 where all the things we are having 1. Take it on left hand side and 2's will be on right hand side. So what is remaining? P1 plus rho GH1 plus half rho V1 square. Half rho V1 square is equal to what is remaining on the right hand side? P2 plus rho GH2 plus half rho V2 square. So apart from writing rho V1, rho GH1, half rho V1 square is equal to this quantity. So what we are following means P plus half rho V square, this term. P, okay, 1, 2 coefficients I am not writing. P plus half rho V square plus rho GH will be equal to constant. Clear? So this is nothing but expression for Bernoullis principle. Okay, the sum of pressure, kinetic energy per unit volume, here delta will cancel, okay, per unit volume, and gravitational potential energy per unit volume will remain constant. Clear? You can copy it down quickly. We'll go to next step. Shall I erase the board? Okay. Clear? So, we have came across two equations. One is nothing but, be able to see here, P plus half rho V square plus rho GH is equal to what? Constant. And before writing this step, one more step I have written. What is that? P1 plus half rho V1 square plus rho GH1 is equal to P2 plus half rho V2 square plus rho GH2. Okay? So let us call this equation as equation number 1 or equation number A and equation number B. Now check. What I will do means, this equation B, I will divide with rho. Okay, equation B divided by rho. So what we will get? P plus half rho, if I divide means rho will cancel, half V square plus GH is equal to what? Constant. Clear? Now I will divide this equation by dividing above equation by G. Clear? So first of all, P plus half rho V square plus rho GH is equal to what? Constant. You should have to remember. Clear? Equation for Bernoullis Principle or Bernoullis Theorem. Clear? So statement of that Bernoullis Theorem, how it will be? Along a streamline flow, okay, along a streamline flow, sum of pressure, okay, next kinetic energy per unit volume and gravitational potential energy, okay, per unit volume, that sum will remain constant. Clear? That is the statement for this Bernoullis principle. Correct now? So, before going to this step, while deriving that relation, we had came across P1 plus half rho V1 square plus rho GH1 is equal to P2 plus half rho V2 square plus rho GH2 is that equation. Correct now? And the next equation what we had written means, by removing that coefficients 1 and 2, we had written that P plus half rho V square plus rho GH is equal to what? Constant. So for that equation number B, I had divided with rho. Clear? So when you divide with rho, you will get one equation. Okay, this is also the equation of Bernoullis principle. Okay. Next, for this equation, now we are going to divide it with G. Yeah. So if I divide with G means, let us check what are the things we are going to get. Dividing above equation by G. First one, P by G, correct, plus half V square by G plus H is equal to constant by G, that is also a constant. So finally we are writing only constant. So these three terms are very important one. Clear? So in this first term, what is the numerator? Numerator is nothing but what? P. P stands for what? P stands for what? It is nothing but what? Pressure. So this complete term P by G is known as pressure head. Clear? What's that? P by G, it is known as pressure head. Clear? Next, here what you are having? Half V square by G. Correct? Here in numerator you are having V square. V means what? V means what? V is nothing but what? Velocity. Correct? No. Half V square by G. This is nothing but velocity. Okay? So this complete term is known as gravitational head. Sorry, what is this? V means velocity head. And third one will be gravitational head. Clear? And if the liquid which is flowing in a straight horizontal manner, that means we won't have from the ground level both the points if they are at same height, then what will happen? So height values will be same, correct? No? H1 value will be equal to H2 value. So what will happen? These two factors, these two terms will get cancelled, rho g H1, rho g H2. So if I treat it as H1 is equal to H2 is equal to H means left hand side also you are having rho g H, right hand side also you will be having rho g H. So rho g H will get cancelled. So remaining terms, what is remaining here? P1, correct? Plus half rho V1 square is equal to P2 plus half rho V2 square. Or how I can write that? P1 plus half rho V1 square is equal to P2 plus half rho V2 square. How I can write this complete term? By removing these coefficients 1, 1, okay, there 2, 2 if I remove means, generally how I can write? P plus half rho V square is equal to what? Constant. Very important one. Clear? P plus half rho V square is equal to constant. Next, if liquid is not moving, clear? If fluid is not moving means velocity value will be equal to what? 0. Correct? No? Velocity values will be 0. So what is remaining? P1 plus rho g H1 is equal to P2 plus rho g H2. P1 plus rho g H1 is equal to P2 plus rho g H2, or P1 minus P2 is equal to rho g H2 minus H1. Correct? No? These are all different forms of Bernoullis theorem. Clear? So P plus half rho V square is equal to constant. This is very much important. Now check in this formula. Here you are having pressure. Okay. Here you are having velocity. Here you are having pressure. Here you are having velocity. Okay. So the sum of P plus half rho V square should always remain as constant value. Okay. So if pressure value is maximum means this V value should be minimum, because the sum of these two should be constant value. If P value came little bit down, okay, P value is lesser than V value, that means P is lesser one, V is maximum, okay, then also this addition P plus half rho V square should come as a constant value only. Clear? So P plus half rho V square should be equal to constant means, from this equation what we are telling means, P, if pressure value is minimum, velocity will be maximum. Clear? If pressure is decreased means, velocity will be increased. Okay? If pressure is increased means, velocity value should be decreased, or velocity value will be decreased, because P plus half rho V square, that complete term, it should have to remain constant, or the addition of P plus half rho V square, pressure and half rho V square, this addition value should be remain as constant value. Clear? Okay, so we are going to discuss analogies like this imagine that you are standing in front of a railway track. Okay, if a fast moving train is coming means, there what will happen, velocity of that fluid particles near the track, okay, that means air will move with higher velocity, correct? No, air will move with what? Higher velocity. So as air will move with higher velocity, and let us suppose near to that track one small boy or one woman or man, someone is standing. Okay, what will happen? Behind that person, atmospheric pressure will be maximum. Why? Means on the railway track, train will be moving, velocity will be maximum, pressure will be minimum. Clear? So at that point, pressure will be minimum, but the person's backside, atmospheric pressure will be acting. But if we compare that pressure with our initial pressure which has been created at rail track, means atmospheric pressure will be maximum. Clear? So due to that pressure, what will happen means that person will be pushed towards railway. Clear? That's why it is dangerous to stand near that platforms. Clear? And one more example also you can take it as in olden houses and all. Clear? Above the walls, above the four walls, they will be putting what sheet. Clear? Like this sheet will be there, no, cement sheet. So if a fast moving wind is coming means, what will happen on the surface of that room? Okay, on the surface, completely top surface I am talking. There what will happen means air or wind will be blowing with maximum velocity. So when a wind is moving with maximum velocity, velocity is maximum. What will happen for pressure? Pressure will be minimum. Clear? So pressure value will be minimum, and what will happen? Inside the room, atmospheric pressure will be maximum. So due to this pressure difference only, what will happen? That roof of that sheets will be blown away. Blown away means it will just flew away. Clear? So this is about Bernoullis principle. Okay? So don't waste your time. Keep studying. Clear? Thank you.